right, my pleasure to introduce Maria.
That's me. Okay, so I'm going to talk about Cocharge. So Cocharge is a combinatorial statistic on Young tableaux, but I'm going to motivate it from geometry. This talk isn't going to involve many proofs. It's mostly going to be definitions and working with combinatorial things. So let's start with the flag variety as motivation. Okay, so the flag variety, I've talked about a couple times in here, is the variety of all flags in some number of dimensions. And right now, let's talk about complete flags. So let's say a flag is something like a chain of subspaces where you take just 0 and then a one-dimensional subspace contained in a two-dimensional subspace contained in a three-dimensional subspace, etc., up to n-dimensional subspace of C to the n, and so this is a chain where the dimension of V sub I is I for all I. Okay? So that's what a flag is, and then the flag variety is FL sub n, or sometimes I'll write B sub n, or for the Borel interpretation. But you can think of it as the set of all these flags, so a lot of times we'll write V bullet to mean this change. So the subscript bullet just means this dot can represent this whole chain of subscripts, and so it's the set of all these the bullets that are complete flags in C to the n. So as a set, that's what the variety is. And then, there's different ways of constructing this as an algebraic variety. But if you know the construction of Grassmannians, you can also think of it as embedded in a project of Grassmannians, right? Because V1 is an element of the Grassmannian of one-dimensional subspaces, and then you have the Grassmannian of two-dimensional subspaces, and so on. And there's, we know this is an algebraic variety. There's a Klucher embedding into projective space. And you can then just show that somehow this containment relation is a closed relation, right? So it's a subvariety of this project of Grassmannians. So the flag variety is, it comes up a lot. So, when you're studying linear intersection problems and things like this, there's a whole field of Schubert calculus studying the Schubert decomposition of the flag varieties, which I might have talked about at some point, which I should if I haven't. I think I will do that for my next Sparks talk. So the thing I'm going to talk about today is the cohomology ring of the flag variety. So in here, sometimes we've talked about the Chow ring instead, and you can think of it as the Chow ring in this case, if you'd like. But the somehow in my field, people just call it the cohomology ring because it's a more general construction. And so this studies the rational equivalence classes of closed subvarieties of the flag variety. And so there's a nice basis of Schubert varieties. So there's, Schubert polynomials generate this. And there's a lot of combinatorics that's similar to the Grassmannian, but I'm going to talk about a different aspect of it today, which is that the one sort of way of representing this cohomology ring is as a quotient of a polynomial ring. So say we're tensor with C, so we have complex coefficients, and we're going to have considered a polynomial ring in n variables and mod out by the elementary symmetric functions, E1, E2, up to En. We're here, EI, or let's say E sub D. One of these E's is just the sum of all the square free monomials of degree D, right? So xi1, xi2 to xid, where these are distinct. I1 less than I2 less than id. Okay. So this is, I think I've actually, a couple years ago, I think I showed why this was the case. The idea, to give some geometry in this talk is that xi is the first Turing class of, so Mark's talked about Turing classes, first Turing class of there's a quotient line bundle you can make for each I, by basically taking, I have vi in here containing vi minus 1, for each of these pieces of the flag, you get a bundle, right? A vector bundle where the fiber over a flag is that vector space, the ith vector space. And if ui is the bundle, the vector bundle such that the fiber over a point, a flag v is the ith component vi, well then you can take the successive quotients and get one-dimensional fibers, and that gives you these fiber bundles that are called, these line bundles that are called ui mod ui -1. And so you get these line bundles, and it turns out the first Chern classes of these line bundles generate the cohomology ring as an algebra, and then these relations, the fact that the elementary symmetric functions vanish, are just due to the Whitney sum formulas or whatever on the Chern classes. What are they? Is that what they're called?
Chern classes?
No, what's the things that the Chern classes satisfy? There's relations. Whatever they call it. Okay, so it gives you these. Okay, by Chern class algebra. So anyway, so this is how you can come up with a very nice presentation of the cohomology ring, and it's something concrete that we can work with. And so what I'm going to talk about now is that since all of these elementary symmetric functions are symmetric, they're invariant under permuting the xi's, right? So there's an Sn action, symmetric group action, on this ring, and instead of writing h star of fln, let's just write r sub n for this ring. It's often called the co-invariant ring. And so Sn acts on Rn by permuting the variables. So if pi is a permutation, then pi acting on an x is just x sub pi of I. So you act on the subscripts of the x's, and that certainly fixes this ideal. And so this action, it's a natural action on the polynomial ring, and it descends to an action on the quotient. Okay, so one interesting thing is that this ring has a really nice Sn action structure. Okay, so when we go over to representation theory now, and we're studying the representations of Sn, I'm thinking of this as an Sn module, and you can ask, how does it decompose into irreducibles, and what does that look like, right? And this is a little bit of an orthogonal direction to understanding the Schubert polynomials. They don't really tell you a lot about the structure of this ring as an Sn module. It tells you more about the geometry. So what Sn representation is this?
I'm sorry, I'm 2 minutes behind.
Oh, sure. Yeah, please stop me if I'm going too fast. I'm giving a quick overview
I
here.
just want to make a remark about the elementary symmetric functions. At least the first one says that the sum of these Chern classes is trivial.
Yes.
And that follows because the last U is trivial, because it's the Cn bundle.
Okay, so I don't have my Chern class fact memorized enough to do this. So let's talk about this. So you're saying the sum of the last vector bundle, Vn bundle is the trivial bundle, right? Because it's constantly Cn. The whole Cn space.
And the Vn bundle is filtered, right?
Yeah, it's a filtration.
By these, and now the Whitney formula kicks in and says that for a filtration, the Chern classes of the center thing is equal to the Chern class of the subbundle plus the Chern class of the quotient bundle. So by iteration, you get that the Chern classes of all of these filtered things add up to the trivial bundles.
Is this what you're saying?
Yes.
Okay, and so then
No,
you're saying...
no, that's not what I'm saying.
Oh, okay.
It's these line bundles. So you've written a bunch of line bundles.
Yeah.
These line bundles are the filtration quotients of UN. Right?
Okay, yeah, I'm not sure how to write that. What's the filtration quotients? What does that mean?
It's just the
So UN
exactly.
This one is one of the line bundles.
That's one of the line bundles.
And
So
then
is the
what do you
next
do?
one. The next one. So
Yes, but I'm not supposed to put direct sums here?
No, not
Okay.
yet.
It's not a direct sum.
It's not
Yeah.
a direct sum, but basically all of the What can I say this?
It's the splitting
It's
principle.
the splitting
You
principle.
can pretend it's a direct sum for the purpose
of the
Turing
Turing classes.
Yes.
That's right, yeah.
And the
So
fact
it's-
that
right.
the last one is a trivial bundle says that the sum of them all are zero, are true.
I mean, so you're just saying there's sort of a chain of vector bundles here, that, you know, the successive quotients are the line bundles.
Successive quotients are
Yes.
the line bundles,
Mhm.
and therefore, the sum of them is the Turing class of the top thing.
Right,
by
so the sum
splitting
of the,
principle.
right, so we have things like C1, UN, okay, so this is a true fact, right? So C1, U, so the sum, there we go.
Yes, that's the splitting principle.
There we go, right.
But UN's a trivial.
But this is 0, right?
Yeah,
So,
right.
that's what
So
we're
that's
saying.
why
And that's why you get the sum of the x of I is equal to 0.
That's what, yeah, I don't know why the sum of the squares equals 0, but.
So it wouldn't be
Not
squares, it
but
wouldn't be
the,
squares, right? It would be like x1, x2
Yes.
plus
I'm not,
x1, x3.
I don't see a trivial way to
There's some,
observe that.
But it must have to do with the fact that C2 of UN is 0, right?
Not clear to me.
This is one of these things that it's in, I know what book it's in, I can give you a reference, right? And yeah, it's like another one of these, what is it?
But it might, it
I
might
don't
have
remember
to
off the
do,
top
this
of my
probably
head.
has to do
Yeah.
with you think UN, tensor product of UN with itself, or the symmetric product of UN with itself. And then that also filters, etc. So that's probably what's going on here. Okay, I believe it now.
Okay, great. Yeah, I didn't prepare like why this was true again, I forget. But I could maybe try this for a different talk. That'd be great. So we're gonna look at what's the symmetric group action on this quotient ring. Okay. And so let's do well, let me state the theorem first. So, but I'm just going to illustrate it with an example. So, as a SN module, Rn is isomorphic to the regular representation of Sn. Okay. So, the regular representation means, CSN as an SN module. Okay, so you take what I mean by this is that you take the sort of, vector space spanned by the elements of SN, right? So a formal vector space where you're like taking formal linear combinations of permutations. So this is, and then the action is by SN acting on the left, okay? And so it's a very nice, first of all, way of writing down the regular representation if we're interested in SN representation theory. And also, it tells us something very nice about this cohomology ring. In particular, it has dimension n factorial, right? You can get this a different way as well. And there's lots of nice bases of n factorial elements to look at, including the Schubert basis, which has a more geometric understanding. But let's look at, just to illustrate this as an example, let's look at R3, which is, so I have 3 variables, x1, x2, and x3. And you're modding out by x1 plus x2 plus x3, and x1, x2 plus x2, x3 plus x1, x3, that's E2, right? And then E3 is the sum of, E3 is all the products of 3 of them, which is just one product. And E4 doesn't exist, right? There's not 4 variables. So you're modding out by these 3. So the sum of the variables, you're assuming is 0, the product is 0, and then this thing is also 0. And what happens, I mean, first of all, one thing you can show right away is that this kills all the degree 4 monomials. So you only have to worry about up to degree 3. For instance, x1 to the 4th, remember this is an ideal. So we're allowed to multiply elements of this by elements of the ring. And so you can write this as, let's take x1 cubed times this element. That gives you your x1 to the 4th. And then you have x1 cubed, x2, x1 cubed, x3, and we need to start using this one. So we multiply this one through by x1 squared minus, we subtract it. And now this has already canceled these two terms with these two terms, but now we have this one left over. And x1 squared, x2, x3, and so we multiply the x1, x2, x3 by x1. Okay, so similar proof can show all degree 4 monomials are 0. And so now you can just analyze the degree 1 through 3 polynomials. So in degree 1, you just have constants. And so it's, 1 is a vector space basis of the degree 1 aspect of this, and that's
The degree 0.
It's degree 0, sorry. Degree 0, yes. I meant constant terms, yes. And I meant, and it's generated by the number 1. And this is just, a copy of C, which is the trivial representation of the symmetric group. And the trivial representation of S3 is often written by a partition with 3 boxes horizontally. Okay. So for those of you who are in 502, you know what I mean. I don't know how much I'll go into the different symbols, but so we get a trivial representation anyway in degree 0. In degree 1, we end up with two basis elements. So I'll just tell you how the 6, you can do more computations of this form if you want, but I'll tell you that in degree 1, we have its dimension 2, and in degree 2, it's also dimension 2, and in degree 3, it's dimension 1. So we have 1, 2, 2, 1, that adds up to our 6 dimensions. And what happens here is, there's lots of different bases we can choose, but I'm going to choose one that really looks like an irreducible representation. So if you're familiar with the some of the constructions for the irreducible representations of the symmetric group, you basically for S3 you look at all the partitions of 3, and this is I draw my partitions in French notation, so I put the bigger numbers on the bottom and then stack the smaller numbers on top of that. And so this is V21 is the span of these two monomials. Now notice these two certainly generate in degree 1 because the only degree 1 polynomial we're modding out by is x1 plus x2 plus x3. And so we had x1, x2, and x3, but then we modded out by one thing, and so we have 2 things left. And these are both orthogonal to this one in some set, right? In sort of a, if you think of it as a vector space with those bases. And so, so this is the sort of natural basis you get. And these correspond to the 2 standard Young tableaux of this shape. Okay, so standard Young tableau is a way of filling the boxes with 1 through 3 in this case, where you're increasing up columns and across rows, right? And so, so there's a way of generating polynomials from these Young tableaux that that gives you this kind of basis in all cases. Now, there's actually another copy of this 2-dimensional representation in dimension 2. And this one's not as obvious to get just from looking at these, but again, you're sort of modding out by one thing in degree 2, but then you also have like this one times other stuff, right? Which is why I don't know, it's still dimension 2. And a basis that makes it look and behave exactly like this one, like to show that you can get an isomorphism here, is the following. And you can ask Kyle all about these. He's been finding bases like this for other cohomology rings. Anyway, there's a way, it turns out, the number of times in the regular representation, the number of times the irreducible V lambda shows up for a partition lambda is equal, this is a general representation in theory in fact, is equal to the dimension of that irreducible for the regular representation. And this is always true for the regular representation, but the dimension is also, like I said, these basis element correspond to the standard Young tableau of that shape. So not only were there 2 basis elements in each of these copies, there were also 2 of these copies, right? And there's actually a way of talking about pairs where you have, 2 different standard Young tableau and also which standard Young tableau you're talking about here. And you end up with a pair of standard Young tableau, and there's a what's called the higher spec basis. This is what I'm writing down for this example. By Ariki, Terasoma, and Yamada. Back in 2005, I think. And they came up with these polynomials that take, a pair of standard Young tableau. Maybe they're different, maybe they're the same, but they have to be the same shape, and you map it to a polynomial of some sort, right? So maybe this one goes to x3 minus x1, because nope. All right, I already know, I'm not going to tell you the algorithm, but it goes to one of these, and it is this one, actually. Okay, so anyway, there's a way of explicitly getting polynomial generators that give you, exactly which representation you're looking at, exactly which irreducible representation of the symmetric group you're looking at, just by taking a pair of standard Young tableau of the same shape. The one in dimension 1 one of dimension 1 in degree 3 is the easiest to write down, well, besides the trivial one. This has just one generator, and it's the product of all the binomials of a bigger index minus a smaller index. So this is called the Van der Waals determinant. And you can see how does S3 act on this. If you switch any 2 of the variables, like if I switch x2 and x1, it negates this and it switches these 2. It just negates the whole thing. So any transposition is going to negate it, and this is the sign representation, which is corresponding to this vertical shape. So, okay, so that's like a big analysis, right, to see what the actual decomposition is. And there's easier ways to see this. I mean, you can look at the character and just say, well, it's the same character as the regular representation. But what's interesting is that we have a graded ring here. The interesting thing about cohomology is we study the graded pieces. And so this isn't just the regular representation, it's a regular representation with a grading. We care about which irreducibles appear in which degree, right? So this, the trivial was in degree 1, there was 2 copies of the what is it called? The standard representation and degrees 1 and 2, and then 1 copy of the sign in the highest degree. So that kind of decomposition is what I care about. Question?
So does Poincare duality kind of correspond to transposing tableau?
You're asking me basically if you flip the degrees around, do you always transpose the tableau? I don't think so. I think it happens in this case. I don't think it's that nice.
Okay.
Why do I not think it's that nice? I think because Cocharge isn't that well behaved. So, yeah, for R3, there's a lot of really nice things that happen with n equals 3 that don't happen, I think, as soon as you get to n equals 5. This one does look really symmetric, but I think the other ones don't. But now I'm not 100% sure of that. I'm just like pretty sure. I think I looked into either this or a similar question and it was false, but I don't remember. So I'll get back to you soon. Yeah. So let's see here. Okay. So this is a lot of information, and so we want to encode it in a generating function because that helps us write things down in a simpler way. So let me talk about the generating function we use to talk about what degrees each irreducible shows up in.
So this is a way to see the regular representations which is C bracket S3,
Yes,
as a graded.
as a graded representation.
Yeah,
Exactly.
yes.
It introduces a grading on the
Yeah,
regular
we're
representation.
giving.
Yeah. Just by the grading, but just by the degree of the polynomials, right? Which is also the degree of the cohomology, right? Okay. So so let's talk about a generating function for this. And it's really a generating function combined with a symmetric function. But it's the Frobenius, the graded Frobenius series is what we need. So what the Frobenius series is in general, if you have a graded representation, now this is any R, not just Rn, right? If you have a graded ring where you have, the d greatest piece is some vector space. Say this is a graded Sn module. Okay. So then we define prob q is going to be a q series, a generating function in the variable q of R, to be the sum of overall d here of, well, I'm going to have to define a different Frobenius. Frobenius of Rd q to the d. So you're putting some coefficient here on q to the d, where that coefficient is, if you have, this is some non-graded representation of the symmetric group. And if you break it into irreducibles, if you have v lambda, irreducible v lambda occurring with multiplicity c lambda, then you just map it to c lambda times sum of c lambda times the lambda Schur function. Okay. So we don't actually need to know anything about Schur functions here. Just you can think of them as a black box variable that's actually just there to represent how many copies of that irreducible you have, right? But anyway, you can either think of it as a generating function in Q whose coefficients are symmetric functions, or you can think of it as a symmetric function whose coefficients have Q powers in them, okay? So that's what this Frobenius series is going to be. And so what it is for R3, let's do this here. So let's remember we have a trivial. Maybe I'll put that up here. Degree 0. We have a trivial. That means that our Frobenius series, so Q of R3, or this one that we just decomposed, is you have a S3 in degree 0, so Q to the 0 times that. And then for degree 1, you write Q to the 1, and then you have a S21 and Q squared S21 and Q cubed S111. Okay. I should warn that these, if I take, say, the degree 2 piece in a general Rn, it's not going to necessarily be irreducible. You're going to have several Schur functions for each Q in general. This one is just, again, very simple. A lot of times we'll group by, okay, where does the S21 occur, and we'll say this is Q plus Q squared. We'll factor out that S21. That's usually how it's written. So I want to just pause here and make sure this makes sense as a construction, because that's the main thing we're going to be analyzing for different cohomology rings. Makes sense? Any questions on how we arrived at that? Okay. Okay, so I'm going to state now the general formula for Frob Q of Rn. And again, notice this notation is going to save me from writing a big table of degrees with a big table of irreducible representations. So let's just write down now a combinatorial formula for this. So So say we want to decompose, remember again, this is the cohomology ring of the Flag variety in dimensions, and we want to understand its decomposition into irreducible SN modules. And so here's the formula. You sum over all partitions lambda of n, so that little thing means it's a partition of n, and of the sum over, say T is a standard Young tableau of shape lambda, right? So we've seen standard Young tableaus here before, where we just start filling the numbers 1 through n outwardly, starting from the inner corner. So that's an example of a standard Young tableau, and you take Q to a statistic, which I'm going to call comaj of T. Maj is a common statistic on Tableau and words that people study, and then comaj is just a slight modification of that. You have S lambda. So the point is this coefficient of S lambda is a sum over Tableau of a certain statistic on the Tableau describing the Q powers. And the comaj statistic is going to be the, descent of a Tableau is a element I that's in a lower row than I plus 1. Okay? So what are the descents here? Let's circle the descents in this Tableau that I just made up. So 1 is in a lower row than 2, so 1 is a descent. Okay? 2 is not in a lower row than 3. 3 is in a lower row than 4. 4 is in a lower row than 5. And 5 is not in a lower row than 6, but 6 is in a lower row than 7. Okay, so that's all the descents. And then the comaj of T is the sum of over I descent. If I is descent, you add n minus I. So maj is where you don't do n minus I, you just do I. Okay, so that's the usual maj statistic on Tableau. And you just need comaj because, I don't know, we're in cohomology or something. That might be where the Poincare duality comes in, right? Where you switch, I'm doing cocharge, but there's also such a thing as charge, and it's just the reversed, exponents. So yeah, so you sum over all the descents of n minus I. And so if we want to do this for this example, this, as comaj equal to, well, we take n is 7, and we take 7 minus 1 is 6, and 7 minus 3 is 4, 7 minus 4 is 3, 7 minus 6 is 1. Which actually, so this example happened to have the descents equal to their complements as a set, but that was a coincidence, I didn't plan that. And so this is 14. Okay, so sometimes you'll see for big N, you get quite large Q powers. You'll get a Q to the 14th in there times this sure function. And so that gives you data of which, where the irreducible will show up. So comaj is a very special case of cocharge. And so cocharge is the generalization I'm going to talk about. And maybe let me just show you a different way of computing comaj to motivate the cocharge. So rather than circling all the descents and then computing n minus I and adding it up, there's a easier way we could do this. So let me copy this Tableau again. So what you do is you start at the 1, and we're going to label it with a subscript of 0. So the 1 is always going to sort of contribute nothing to the comaj in this way of calculating it. So start at 1, label with a subscript of 0. Okay. And then, now look for the 2, or look for the next number. If we went up to a higher row, right, we increment the label. And so in some sense, okay, the 2, we went up from 1 to 2. That encodes this descent over there. And in some sense, that label is going to be incremented for the rest of the time. So you can imagine in your head, we're adding 1 for everything that's not 1. Because we had a descent, and that's adding that 6 is the 7 minus 1. Everything except the 1 is getting labeled. Except, just keep these extra 1s in your head for now, because we're also going to increment whenever we get to a descent. So now we look for 2, right? Or sorry, now we look for a 3. If we went up, increment the label and so on, right? But we didn't go up from 2 to 3, so we just keep that 1 there. But the 3 now goes up to 4, and so now our new label is 2, right? And that's saying that the 3 is a descent, so everything above the 3 needs another 1. So imagine you had 1s on all these things, and now we add another tick mark, right, for everything above the 3.
Yeah.
But to me, I'm just incrementing the label as I search for the 4, and that's more efficient. 4 goes up to 5, so I add another 1, and then I don't add anything going to 6, and I do add something going to 7. And then it's the sum of all the subscripts, okay? So, so that's 3 plus 4 is 7, 8, 9, 10, 11, 12, 13, 14. So same thing, right? Just a different algorithm for computing the same thing. And so this is actually called the cocharge of this tableau as well. So this is the cocharge way of computing it. But cocharge allows us, it's a much more general algorithm that we can generalize to other tableaux. Okay, so why do we want to generalize this? Well, because I've talked about Springer fibers in the past here. When Martha Prekop visited, we talked about Springer fibers and Hessenberg varieties and all those things. And so there's lots of variations on the flag variety and subvarieties of the flag variety that are being studied right now, whose cohomology ring we don't understand as well as the coinvariant ring. So what we want is some generalizations of this.
Professor, really quickly.
Yeah.
So comaj is cocharge.
It is in this case, right? So comaj is only defined for standard tableau. Cocharge is going to be defined on semi-standard tableau
Okay.
of a certain type. So it's more general. It's just, somehow the maj is always like the sum of the descents kind of statistic. And I'm saying this is like a cocharge method of computing comaj. They agree in this case.
Okay.
But they were defined on different things in general. So, so let's talk about the Springer fibers. Going back to some geometry here. So a Springer fiber is if you have, B mu is a subvariety of the flag variety defined as the set of all flags, such that a certain matrix, n mu, sends each part of the flag into itself, okay? Here, n mu is just a nilpotent matrix whose Jordan blocks have size given by this partition mu, right? So this is, for instance, let me just give an example. You'll have like an upper triangular matrix with 1s on the diagonal, and if the 1s are here, then the blocks have size 3, 2, 2, and 1. And so this corresponds to the partition. So mu is 3, 2, 2, 1. Okay. So we've talked about the Springer fiber in a little more motivation, and I talked about it in a different talk maybe earlier this year. And it's a subvariety of the flag variety. And what's really nice is its cohomology ring is actually a quotient of the Rn that we studied. Okay. So I kind of want to keep this here. Let me just erase this n mu. It's just a nilpotent. So let's define R mu to be H star of B mu. This is also C adjoint x1 through xn, but mod other stuff. So more general stuff. I don't want to write down, I could just also write Tanasaki. So Tanasaki, back in the 90s, found explicit generators for this ideal. And it's, same ideas. I mean, these are still the same Turing classes in some sense, right? It's just that because we have this condition, we have more things to mod out by. And so, so he proved the generators work, and then De Caccini and Frattesi they studied the SN action on here, and they showed that this Frobenius character is actually a symmetric function that was already known, called the Hall-Littlewood polynomials. So they're written H mu. These are called Hall-Littlewood. These were already studied for many years before Tanasaki and De Caccini and Frattesi came along. And they're generalizations of the Schur functions and things like this, right? So these then, in turn, also already had a combinatorial formula known, similar to the comaj formula, by Lescaut and Schutz and Roget. And I also want to put Butler here, because Lescaut and Schutz and Roget proved the formula for an explicit combinatorial formula for these Hall-Littlewoods, but their work was so unreadable that a lot of people weren't really convinced of the proof until Lynn Butler wrote an entire book analyzing every step of the proof and working out the details. And so I would really say that the real proof is in Lynn Butler's book on Hall-Littlewoods. And so so their formula is, let's see where I want to put this. So I want to keep this example up because I'm going to do Cocharge in more generality. So the formula is Frob Q of R mu is the sum over lambda of the sum of T being a semi-standard Young tableau. So semi-standard means that you are allowed to repeat numbers in rows. So rows are weakly increasing, and columns still have to be strictly increasing going up. So you have semi-standard Young tableau now. Of shape lambda and content mu. What this means is, so you still have this partition as lambda, and mu is the number of ones, number of twos, etc. in your tableau. So your tableau is going to have more ones than twos and more twos than threes and so on. So you have a fixed sort of number of ones and number of twos and number of threes that you fill your lambda with. And then you have Q to the cocharge of T of S sub lambda. And so, so then the question is, what is this Lescaut, Schutz, and Roget cocharge statistic? And it generalizes this comaj formula. And the way you do it is you, let me see what I can do in 5 minutes. So you still start at a 1 and label it a 0 and then label a 2 and then label a 3 and then label a 4 and so on. But the question is just which one do you pick up first, right? And so cocharge, what's easiest to define is cocharge of a word, where you take the reading word of this tableau. So you read a tableau from left to right and top to bottom like you would read a book. So you take the reading word. And then you define the cocharge of a word to be the sum of the cocharge of the standard subwords, which are usually called WI, And so the standard subwords are formed by searching in reverse order for a 1 and then a 2 and then a 3 and so on. So in other words, my first standard subword is I start at the end of a word and I search to the left, and the first one we circle. And then we keep searching for a 2. And then we keep searching for a 3, but we reach the end of the word, so we cycle back around. Okay, we circle back around to the beginning and we search for a 3. And then we search for a 4. And then we cycle back around and search for a 5. And that is my first, we keep going until we can't, we don't have any 6s. So that's the first standard subword. And then the second standard subword is you get rid of all that and you start over and you search for a 1. So I'll underline it this time. And then I'm searching for a 2, and I can't use the 2 we already used, so we come back around and we get this 2. So that's a decomposition into 2 subwords that each have the numbers 1 through something exactly once, right? And then you just compute the cocharge on each of those subwords, okay? And the cocharge, this cocharge, right? So this is generalized cocharge, is you just add up the cocharges, or the comages, or whatever you want to call it, on each of these standard subwords. If I wanted to do it on the tableau, I'd just sort of read this way, and I would label my 1 with a 0 and my 2 with a 1, because I went up. And then I loop back around. I did not go up to a 3, so I keep my subscript the same. And then I increment it up to there, and then I don't increment to 5. And then I start over. So now I label this 1 with a 0 and this 2 with a 0. And you add up the subscripts, and this has cocharge 2 plus 2 plus 1 plus 1, which is 6. Okay, so my goal was to define cocharge today, and I defined it. That's cocharge on a semi-standard Young tableau. And it has so many nice properties that it looks like this really complicated, like spinny sort of statistic, but it's actually the unique statistic that is on words that is compatible with what's called Knuth equivalence. People in my class know what that is. And also, it has this nice property called cyclage, where if you take a number that's not 2, sorry, that's not 1, if the number on the end is not 1, you can like swing it around to the beginning, and that decreases the cocharge by exactly 1. And if you have a 1 on the end, then you have to like deal with it some other way. So there's like sort of actual moves that simplify the cocharge where you can actually straighten a word until it's like increasing it from left to right, and then you get 0, and so you just see how much you decreased it by each time. So those were all like fun combinatorial properties I had planned, and I don't have time to say. I was also going to just mention that me and my collaborator Sean Griffin are working right now on a further generalization of this formula. He has these varieties called the Delta Springer varieties, which are further subvarieties of the Springer varieties, where he has an extra condition in here that comes up, when you're studying all kinds of symmetric function theory, and they were, modules that varieties that were just defined for this property, but we didn't know the Frobenius character, and we came up with a formula like this, and it is true according to the computer, and still is not known to be true according to math. So we don't know how to prove it yet, but this is like the new result that I was working on, and so I wanted to tell you about the cocharge background of that. So I think I'll just stop there.
Questions?
Yeah.
So if there is a cocharge, presumably there is a charge?
Yes.
Does that relate to any of this geometry story at all?
Not really. It's, it's like Mark was saying, like if you want to do Poincare duality and reverse all the degrees, then you get charge instead. That's all it is. And so, so not any more than cocharge does, right? It's like, I don't know why charge was, I think charge is just a little more natural because as combinatorially, how you compute charge is instead of going up by 1, like in the word, instead of going up by 1 when you don't wrap around, you go up by 1 when you wrap around the edge of the word. So like wrapping around like charges you up, and it's like a more natural thing to do, rather than like not getting charged up when you wrap around and getting charged up when you don't, right? That's the only reason it's cocharge instead of charge, because the charge is the more natural combinatorial thing to talk about. And then cocharge is the one that corresponds to the cohomology. So that's all it is. So, yeah.
I just had a general question. What does the word statistic mean?
Oh, I do use the word statistic a lot. When I say statistic, I mean I have like a set of combinatorial objects of some sort. And I have a statistic that maps them to like usually Z plus,
Z plus,
sometimes Z.
okay, yeah.
Actually, I should really say not plus. Like, and right, you can have 0
Yeah.
as your statistic. And so Cocharge is a statistic on Young Tableau. Maj is a statistic on Young Tableau. There's lots of other statistics on Young Tableau, like there's an inversion statistic or whatever. There's just lots and lots and lots of statistics on permutations. And in fact, Angela, what's her name? The one that, so James has a visitor right now. Angela, she's staying in Alexander's old office, and you should go say hi. She studies combinatorial statistics on permutations. So it's, yeah, there's a whole field of combinatorial statistics and understanding.
It's like something you're counting, kind of.
Yeah, well, it's like a refined counting. I mean, it's good for graded things because, you know, any combinatorial statistic gives you this generating function of like how many of your object have that output for its statistic.
Right.
And so it's instead of just counting how many combinatorial objects there are total, how many Young Tableau there are or something, you're counting them according to how many have a certain output for the statistic. And that's it's sort of a more refined counting. That's right. Yeah.
Any other specialization of interesting specialization of from QR?
Oh, lots of, wait, for specializations, you mean like
Like a
interesting Frobenius characters of other rings?
like the plugging in numbers to Q or X, and then recovering some
yes.
geometry.
Yeah, sure. Well, okay, so first of all, plugging in Q equals 1 is always the thing that undoes the grading. So if I plug in Q equals 1, then I just get the ordinary Frobenius characteristic, which is just going to tell you that basically Rn is the regular representation, right? Because the Q power keeps track of the degree of your graded representation, and so if you plug in Q equals 1, it gets rid of all that. If you plug in Q equals 0, you get the bottom degree, which in this case is not interesting. It's trivial. But in other situations, that might be. You generally don't want to plug in like Q equals -1, or, I mean, sometimes a root of unity or something, like if you want to filter for, this is just a general generating function trick, right? If you want to filter for just the even degrees or just every third degree, you plug in the roots of unity. So you could plug in -1 and plug in 1 and add them up or something like that. As far as plugging in x's, the one, you know, you have to be careful because the x's are different here than they are here, right? So if I think of the Schur function as a polynomial in n variables or something, these are not the n variables that are used to define these rings, right? I almost want to call them something else. But let's call them like z1 through zn or something, right? Then yes, you can make substitutions here that mean something. There's a really famous substitution where you do that. You substitute the powers of q, and it just makes a nice combinatorial formula with like a product. So then the q series actually factors. I don't remember the product off the top of my head, but there's a lot of really nice things you can do. But I don't know. Yeah, I mean, usually the goal is to just understand what the formula is, right? Yeah. Cool.
All right, thanks.
Yeah.